So we've technically started the lecture. What I was going to try and show you is, oh, it's a bit loud. So last week I was hoping to show you how easy it is to send a spam email. Just need to make sure I don't have anything that looks. Sorry, I know you can't see anything. It doesn't. Okay, so maybe that's not a very good idea. Let me just see. How do I get rid of this? Let's see, that worked. There was a token on there. If you copied it, I'm not going to say it's recorded, but I can change it. It was an authentication token that was on there, which I use for something, but I can change it, so that's all right. Anyway, so last week I was going to kind of show you how easy it is to use SMTP to send a spam email, right? So this is just a traditional part of the course we've always done. So you can look at the RFC for SMTP. It's quite simple, and then so all I'm going to do is just follow it really, and then show you why it's so easy to send a spam email. So first thing I'm going to do is I'm going to connect to the. I know this is because this is the only mail server that allows me to do it. Telnet mail.elec@adelaide.edu.au. You guys can't see anything, of course not. Sorry, apologies. So I'm going to connect to a mail server. The reason I'm using the ElecEng mail server is actually I'm an engineer, that's my background, although I'm in computer science, is because this allows me to telnet, right? The other ones I tried didn't. Okay, so the port is 25. So essentially now I'm connected to the mail server in ElecEng, right? So and now all I'm going to do is follow the SMTP protocol. So the first thing you do is you say hello, ELO. I can pretend to be whoever I like. No wait, ESMTP, where's delete? So it should be HELO. I can say pretend to be whoever I like. If I like, I can say hello Google, and usually it says. So it says, hello Google, pleased to meet you. So that's just a greeting. And after that, I want to say mail from, who is a mail from. So again, I can pretend to be whoever I like because the mail server has no way of authenticating me, right? I could potentially put, CNA at whatever I want. I don't know. Something fun, CNA.com, Donald Trump, Prime Minister, whatever you want, right? So hopefully I spelled that correctly. And then the next line should be RCPT to and receipt to, so I'll send it to my ElecEng account. So who am I sending to? ElecEng, eleceng.adelaide.edu.au. So the recipient checks out, so far so good. And then I'm going to type in my data, right? So it ends with a dot, so that's good. So data 2, so when you get an email, you see who is it to. I can put whatever I like, me@me.com. And from, again, I can be whoever I like. Okay, I can be John at okay. Hopefully I don't get trouble writing this. And So I have to from subject, subject, greetings. Then you need a blank line for the body. Hello, spammer here. Is it double M? Who knows spellings better than me? Spammer. Yeah, thank you. And then finish with a dot. So message accepted for delivery. Yay, good news. Now I have to reveal my Gmail account. To you guys, it's going to get recorded. I could delete it, right? Yes, I can. I'm guessing it's just probably in spam, maybe. So here it is, right? Clearly, I didn't spell president correctly. But if I open my email, lucky, you will see that it says it's supposed to be president@whitehouse.com, but so it looks like it came from, right, anyone you want it to be, right? Okay, so it was from and to me@me.com, right? So you can see it's very easy to send a spam email, right? It requires, because there's no way for the mail server at electchange.com to authenticate me or verify anything what I'm saying, right? Yeah. So yeah, spam's going to be around for a while. Okay. Any questions? Was that worth doing? Was that cool? No, cool. All right. You're not impressed? Don't go and spam people, especially me. You can see I have 1,900 messages I haven't even read. They're not spam. Okay. I hate email, really. I use a messaging platform to talk to my students now. All right, so remember where we left things off? Okay. So we started talking about document camera. So we started talking about security, and then we talked about spoofing, denial of service attacks, and a whole bunch of stuff. And we said that any protocol that we looked at in this class can be exploited somehow, and it's very easy to do that, right? Okay, because all of them have security vulnerabilities, right? Okay, and whether it's DNS, whether it's handshaking for making a connection, whatever it is, right? So need you guys to be aware of that. Then what we did was we sidetracked and said, let's look at some of the tools we could use to do security with. And we talked about, where I stopped was talking about the characters we typically use in terms of talking about security. What is plain text is a message, ciphertext is a thing that's encrypted. Encryption is a process, like a function you apply to scramble stuff. Decryption is a process or a function you apply to unscramble stuff, right? That's kind of where we stopped off. And the thing with symmetric key was that both parties use the same key, okay, to scramble and unscramble, right? And then the simple example we came to was this one. So this is you probably don't want to do this. So this is called a substitution cipher. So you have all the letters in the alphabet are being substituted. So here A will be represented by an M, B will be represented by an N, right? So if Bob wants to declare his love to Alice, Bob would write that and then substitute I, so in this case for an S, right? So that's why it's called a substitution cipher. So this will be your ciphertext. So, so in this case, what is the key for this cipher? What do you want to keep secret? What does Alice and Bob both need to know to encrypt and decrypt? That's right, you just need to know the mapping, right? So your key is the mapping, right? Okay, so a long time ago, that's what people use. Like, you may have seen movies, right? Spy movies, I love spy movies. So, people use like a novel, right? A page in a novel, right? Or a paragraph, and that's the starting point for the substitution cipher, right? So if you knew the book and the page number, then you could just decrypt the message, right? And then because you use a different page and different book, so your substitution kept changing, right, every time. So that's called a one-time pad. You never use the same substitution mapping again, right? So this is not very good security, right? Why? How easy is to break this, right? If you saw this, sorry, that wasn't very good. If you saw this part, right, could you figure out the message? How easy is it to break it? How easy is it to brute force it? What's the complexity of an attack? How many trials would you need? How many different things, how many times would you need to try? How many possibilities are there for the letter S? Okay, right. So the complexity is 26 factorial, right? Yes? Okay. So that's, for computers these days, to do a brute force attack, trial and error, won't take very long, right? What else could you do to break this? What other information could you use? What do you know about the English language? Guess the common letter, right? The most frequent letter, what is it? What do you think the most frequent letters are? E, right? So you could probably go, look at a large method. You can see this particular G occurs so many times. I'm going to guess a G is an E, right? So you could go that way. So you can use the frequency, right? Okay? So yeah, it's not a very good example, but but it is a symmetric key because the key is the mapping and both parties need to have the mapping, right? Okay? So here's modern day examples of symmetric key encryption are this stuff here, right? So you may have heard of the advanced encryption standard. So it's a standard. It doesn't tell you what the algorithm inside is. So so there was a contest, an algorithm is chosen, and then now it's a standard. So AES is a standard, and there's a 256-bit key version of it, which is what you should use, which is the recommended key length, because in your previous example, right, it was very easy to brute force to figure out the key. You only had to try 26 factorial times, right? But if the key size was very large, 256 bits, then how many different keys do you need to try to figure out the right key in a brute force attack? How many keys do you need to try? How many possibilities are there now? Sorry? No, now we have a key of 256 bits. How many different numbers are there for the key? Possible numbers are there? 2 to the power 256, that's right. Right, that's a really big number, right? Before it was 26 factorial, right? But now it's 2 to the power 256. Even if you use, a cluster of computers, right? You're going to be brute forcing this key for a very, 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 very long time, right? So it's quite safe, right? So there are easier ways to break things. Nobody breaks a key typically these days. It's easier to just bribe someone, or just use phishing attacks, right? Do you know what I mean? That's so much easier to do that than, most of the security vulnerabilities are not because of the key was hacked, right? Rarely, ever, right? Most of it is because of software vulnerabilities, programming, bugs being exploited, intentionally put or otherwise, right? Or because of phishing attacks, somebody just clicked on an email or, something like that, or used a bad password, right? Because in terms of key security, this is humongous, right? Okay, you wouldn't be able to compute this for 500,000 years. Right? Okay, so some of the modern examples are AES DES, data encryption standard. So this was broken in like 56 hours in '96 because it used a key which was 56 bits. So that means the key complexity is 2 to the power 56. What that means is there are 2 to the power 56 different possible keys. A modern computer, a laptop could probably crack that, right? Okay, but if you had extra information, that you could make that faster. So this is too short. So triple DES means doing this 3 times. So the key is now 3 times 56 bits, right? RC4 is another example of a symmetric key cipher. So, but if you want to use this stuff, the recommended one is whatever is the advanced encryption standard algorithm is, with a key size of 256. This is like, military grade security, right? This is the best way we know how to encrypt stuff today, right? So there are a whole bunch of different block ciphers. I mean, if you're interested, we can talk some more. So this one is called a. I'm not going to ask you at the exam, but you know, just because I can. So this one's called a block cipher, but there are also a different type of symmetric key ciphers called stream ciphers. Now, the difference is simple, because if it's a block cipher, you take the key and the plain text and you get out ciphertext. So this could be AES, for example, right? But if it's a stream cipher, what happens is, so you have a key which is kind of like, and then some initialization vector that goes in, and this generates a key stream which you then XOR with plain text to get your ciphertext. So this is called a block cipher. The reason that it's called block cipher is because what you get is a fixed size block of ciphertext, maybe 256 bits. But with stream ciphers are fast, but there isn't a very secure stream cipher out there, right? So people almost always end up using block ciphers, right? And it's hard to prove the security of a stream cipher, but there are good ways of analyzing block ciphers. So typically people use block ciphers, although stream ciphers are really fast, right? Okay, just a little bit of info, right? Okay, so there is, if Alice and Bob, let's say, wants to send a secure email, right? If they want to send a secure email, now all they have to do is essentially have a private key, right? So secure email, so what we are going for is to achieve confidentiality. What that means is that we want to encrypt. So we don't want Trudy to figure out what the message is, right? So we want our messages to be confidential. Only Alice and Bob can read those messages, right? So in this case, it's great because we have a private key, and then Bob has the same private key, right? Okay, same private key, and what you do is you take the private key and you encrypt it. So remember I told you this was encryption, right? And then Bob receives the encrypted message, takes the same private key, right, and does decryption and recovers the message. So if Trudy was to look at the message, what she would see is this. This is your ciphertext, right? Garbled up stuff, okay, that you wouldn't understand because it's been encrypted, garbled. So the problem with this approach is the private key, right? How do they first exchange the private key, right? This works okay if it's only two people. Maybe they can meet secretly. Have you guys seen movies, right? So have you seen, you know, like armored cars with a guy with a briefcase, you know, going from place to place, being protected? He's carrying a private key, right? Because, you know, sometimes that's what you got to do. You got to protect the private key, right? And you have to physically transport it. If you don't have a secure communication channel to start off with, how do two parties exchange a private key? I mean, think across two countries. You'll have to fly a plane, you know, with fighter jets around just to make sure the private key is not lost, right? So exchanging the private keys, that's a problem, right? What if you increase the number of people to a million people that want to communicate with each other, right? So think if you have n people that want to communicate, right, with each other, okay? Each of them needs to communicate with each other. I can't draw enough lines, it's getting confusing, right? Okay. N1, N2, N3, blah, 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 and N, right? So that many people want to talk to each other. Okay? How many private keys will you need? Huh? Sorry? Catalan numbers. No, I mean, think, it's not that hard. So you have N people that want to communicate. This guy needs how many keys? Huh? N plus 1. No, he has N minus 1 people to communicate with, right? Yeah? So you need N into N minus 1 keys, right? Yes? Each person needs N minus 1. There are N people, yeah? So if you had 1,000,000 people, you need million into million minus 1. So 1,000,000 times 1,000,000. Is that feasible? And those 1,000,000 people will need to travel in armored cars, you know, and meet and exchange briefcases, right? So this is called the key distribution problem, right? Okay, so that's a classic problem, key distribution problem. How do you distribute the private key? But good news, good news, good news. There's always good news. So this problem was kind of solved by using what I call private keys or Diffie-Hellman key exchange protocol, right? So the idea was if you had two parties who needed to exchange a key using an insecure channel, how would you go about doing that, right? So the way it is done by using private keys, without going into too much detail, let me just explain. Sorry, what did I just say? Did I say private keys? Sorry, public key. Right, I apologize. I have this dyslexia where I think something but I say something else. So the way to solve the key distribution problem is by using what's called Diffie-Hellman key exchange, and then we can implement that by using public keys. Okay, right. So let me give you an example of what public key looks like without going through all of this stuff. So essentially what happens with public keys is that there are two keys, right? There are pairs of keys. So in this case, if you take Bob, for example, Bob has two keys. One's called a public key and the other one's called a private key. The reason this is called public key is we assume that everybody knows this, right? Okay. So including Trudy knows this key, right? We don't care. You can look it up in a newspaper, put it on a bulletin board, put it on a discussion board, right? But he also has a private key which is secret. Only Bob knows this key, right? And Alice also has a similar key pair. Okay, Alice also has KA plus and KA minus, right? So this is public, and this is private. So when Alice wants to send a message to Bob, right, confidentially, which means encrypt the message so no one can read it, confidentiality, right? What Alice does is Alice looks up Bob's public key. Anyone can look it up, okay? And then uses a public key to encrypt it, okay? Now, so Trudy will know Bob's public key, but you can't use the public key to decrypt this message, okay? Remember, with symmetric keys, you can use the same key to encrypt and decrypt, but with public key cryptography, you have to use the private key to decrypt. But who has the private key? Bob, right? Only Bob has the private key. So only Bob is able to decrypt the message, right? Is that clear? So Trudy can't decrypt it because Trudy does not have access to Bob's private key. Only Bob has access to Bob's private key. So Bob uses his private key right, and decrypts. So now, two people don't have to travel in armored cars, meet in a secret place protected by armored guards to exchange keys, right? And they could be in two different places on a planet. Alice could be in Japan, Bob could be in Madagascar, right? They just need to know where to look for the public key, and we're done, right? Right? Pen pals. Have you had pen pals? A long time ago, pen pals. You guys know the pen pal generation, right? So it's like having a pen pal. You don't need to meet, but you can still confidentially communicate, right? Okay. So any questions with that? Is that clear? Okay. Just a bunch of stuff real quick. So requirements are, of course, we need K+, which is a public key, K-, which is a private key, such that this is possible. It's quite obvious, right? If you encrypt it with a public key, you must be able to decrypt it with a private key. That's a requirement for a public-private crypto system. And given the public key KB+, which is exposed to the entire planet, it should be impossible to compute the private key, right? Otherwise, you're screwed, yeah? Because what that means is that whatever information that you leak or expose should not reveal any information about your secret. Make sense? Right? So some of the examples of public key crypto systems that are in use is RSA, which is named after the inventors, Ron Rivest, Adil Shami, and Adelson, right? And there's also what I call ECC, elliptic curve crypto systems, right? The difference between the two is that for this course is RSA to achieve the same level of security with RSA, you would need a bigger key than with elliptic curve cryptography, right? Okay, that's pretty much it. And the other one would be, of course, so that means you could argue that elliptic curve cryptography is faster because you can use a smaller key, right, to achieve the same level of security as RSA, okay? Here's another cool property that we're gonna need later, right? So RSA has a cool property, which is that it turns out that if you encrypt something with the public key, right, you can decrypt it with the private key, which is what we just looked at. But also, if you encrypt something with the private key, you can decrypt it with the public key, right? So this is a cool property RSA has, right? You can encrypt with either key and decrypt it with the opposite, yeah? Okay, you'll see why this is important when we talk about digital signatures. Okay, remember that, right? We can go either way. Yeah? Okay. Now, so in practice, what RSA is really used for is to exchange session keys. What that means is that use public key cryptography to exchange a symmetric key for the following computations, right? Why do we do that? Because typically, if you want to use public key cryptography, it's heavy, right? It requires calculating the exponent to some very large number, so it's mathematically demanding on the machine. So you don't want to be using public key cryptography to encrypt all the communication that you're going to have, right? So what you do is use public key cryptography to do the key exchange, which is solve the key distribution problem, agree on a symmetric key, and once you know the symmetric key, for the following stuff, use the symmetric key to encrypt, because symmetric key cryptography is fast, right? Very fast, okay? Actually, it's also more secure. Turns out AES is the best way we know how to do things. Right, so let's go back. So we got some tools. We got two tools, symmetric key cryptography and public key cryptography, right? So we're going to see how these tools are put together to achieve some security, okay? How are we doing? How am I doing? 20 minutes, not good. All right, simple protocols. So let's start with authentication, right? Authentication is a service, security service. You want to prove you are who you say you are. Simple protocol. Alice says, I'm Alice. Is that secure? Needed to be quick. No, why not? Because what can Trudy do? Okay, sorry. Imagine that they can't see each other. I'm sorry. So just imagine there's a wall, okay? There's a wall. Bob can't see Alice. Bob is in Japan. Alice is in Japan. Bob is in Madagascar. Can't see each other. How Trudy can just say, I'm Alice, right? Yes? Very easy to fool. Come on, guys. Don't fall asleep on me, all right? Okay. Second protocol. Okay, improvement. What can we do, right? I'm Alice. Ah, Bob has no idea. I hate you. They break up. Okay, so in the internet, from a networking perspective, if Alice is your web browser and Bob is your bank, how would the bank know who you are, who you say you are? Could we use the IP address? No. Why? Yeah, it can be spoofed. Trudy can look up your IP address and send it. It's not going to work, right? So what can we do? Can we use a password? Can we do this? So you send your IP address and password. Is that going to work? Is that going to work? No. Why isn't it going to work? What can Trudy do? Yeah, exactly. You send everything in plain text. So Trudy just sits there, records the information, right? Records everything you say and playback. So this is called a replay attack, right? Why? Because this stuff is plain text, right? Yeah? Even if it's encrypted, what happens? Okay, let's encrypt the password. Does this work? Encrypt the password. Trudy doesn't know what the password is. Well, is that going to work? Why not? Replay attack, who cares what the password is? Record the same information and play it back, right? Bob doesn't know, right? Okay, you record the encrypted password, play back. Poor Bob, right? Okay, what can we do? How can we avoid the replay attack? Any ideas? I wish we could discuss this in more detail, but because I'm running out of time, one way to solve this problem is by using what's called a nonce. Piece of information that's only ever used once, right? A nonce. Nonce means if I use it, I'm never going to use it again. It could be a number, right? Okay, a very large number that I'll use once. So that if I use it, then that means if Trudy records it and plays it back, I know, aha, this was an old message, right? I've seen this one before, okay? So this leads to what's called challenge response protocol, right? So what that means is that first you say, hey, I'm Alice. Bob goes, oh, here's my nonce. Number that's used only once, right? Okay, never used again. So this is a nice little tool in cryptography, right? A nonce, very helpful, okay? So you send a nonce, and then let's imagine they both have a key that they agreed on. So is this symmetric key or public key? Symmetric key, same key, right? So then Alice encrypts it and sends it back, right? Bob goes, Bob decrypts it and checks that it's the same R, right? Okay, is this the R I sent? If it is, you must be Alice, because only Alice would know the secret key, right? Yeah. So if Trudy was to record this message, can she play it back? Can she play it back? Is it worth recording this message? Will it work if she plays it back? It won't, because why? I just said, what's the property of R? Use only once. So that means if Bob's never going to use it again. So there's no point recording it, right? Because Bob's never going to send that R to Alice again. Okay, use only once, right? So simple security property guarantees security, right? Beautiful, yeah. Property of R, used only once. But what's the problem with that? You know the problem with that, right? Because we still have to solve this problem, right? Yeah, but we know how to solve that. How do we solve this problem? We use what? That's right, public cryptography, yeah. You guys are going to be security experts in 20 minutes. Okay, so that's pretty cool. So we can solve this by using public-private key cryptography, right? So that's brilliant. So it says, hey, I'm Alice. Here's my nonce, right? And then Trudy goes, yep, okay, I'm going to encrypt it with, not Trudy. I'm not on Trudy's side. I am totally on Alice's side. So Alice encrypts it with her private key, okay? Right, and sends it to Bob. Now remember that Bob can look up Alice's public key, right? Because it's public, okay? So Bob just needs to look up KA plus, which is the public key, yeah? So Bob looks up the public key and then decrypts it and says, oh, I got my R. And then goes, well, only Alice knows Alice's private key, right? So only Alice could have encrypted this message, not Trudy, right? Yes? You agree? Because I used Trudy's public key and then I got back my R. So only Alice could have encrypted this because only Alice knows Alice's private key, yeah? Okay, so what that means is that, yeah, okay, cool. So there is a problem with this, and can you tell me what the problem might be? What is the one step in this security protocol that could lead to a failure? What does Bob have to do? What does Bob need to verify that it was Alice who encrypted it? What's the one piece of information Bob needs? Come on, guys, it's right here. Yes, public key. So he has to look up the public key, right? And this is a potential weakness of that protocol, right? Simply because where does Bob go to look it up? I don't know, website, right? Okay, Trudy can replace that, right? Yeah, okay. So we'll see why this is a potential weakness to this whole protocol, okay? Here's what could happen. So this is called a man, or if you politically correct, maybe man or woman in the middle attack, right? So Trudy poses as Alice to Bob and Bob to Alice. This is how it might work, okay? So let's see if you can follow this through. Now, imagine that Trudy is sitting in between, I don't know, somewhere in the Maldives, right? Intercepting communication between Madagascar and Japan, right? Okay, she's in Maldives, beautiful place, right? Tropical islands. Okay, so Alice goes, I'm Alice. Trudy intercepts the message, and no problem, plays it back to Bob, right? Bob goes, okay, here's my nonce. Here's my nonce. Now Trudy intercepts the message because she's cut the wire or something, I don't know, right? Okay, she's sniffing through the air. And then what does Trudy do? Trudy takes R. This is Trudy. Trudy encrypts it with her private key, right? So this is Trudy, okay? And sends it to Bob. Now Bob has no idea that this came from Trudy, right? Because Bob's in Japan, yeah? And she's in Madagascar, or the other way around, forget now, confuse myself. So then Bob goes, well, fine, but I need to look up your public key, so send me a public key, right? So Trudy sends her public key. This is Trudy, okay? So that means this computation on Bob's side is going to succeed, right? Because Trudy just substituted her public key, right, to Alice's public key, right? So as far as Bob's concerned, Bob, who cannot see anything on this side, totally, is going to go, okay, so you said you're Alice, I send you a nonce, you encrypted it with your private key, I got your public key, I'm going to decrypt it, I'm going to get back R. Bob ends up thinking I'm talking to Alice. But on the other side, Trudy replays this same message to Alice, sends a nonce, then Alice now encrypts it with her private key. Trudy goes, send me your public key, right? And then Alice sends back a public key. Now, Trudy can obviously decrypt this message, right, if she wants to, yeah? So Trudy gets hold of all the messages that are going between Alice and Bob, because Bob is now using whose key? Right? Bob is using Trudy's stuff, right? Because Trudy substituted her public key and private key, right? And Trudy now substitutes her public key and private key. So that means here Bob ends up sending messages to Trudy. Trudy can know what those messages are and then relays them to Alice. And Alice sends message to Bob, Trudy intercepts them, and Trudy knows what those messages are and sends it to Bob. So that means Trudy is sitting in the middle, essentially, listening to all the messages that are going back and forth, right, between Alice and Bob. And if Trudy is very clever, she doesn't need to interfere, right? All she needs is for Bob and Alice to know that to think that they're talking to each other, right? She can just decrypt and watch the messages that are going back and forth, right? Okay. So essentially, Trudy gets hold of Trudy is able to recover all the following messages because now Bob ends up using Trudy's public key to encrypt messages, right? And Trudy can decrypt them. Okay, and then Trudy takes that message, encrypts it with Alice's public key, and sends it back. Alice has no idea. Alice thinks, oh, this must be Bob that did that. No, it was Trudy sitting in the middle that did that, right? Okay, so Trudy gets hold of all the messages back and forth, right? So the key failure here is this step, yeah? This is the failure for this protocol, right? Okay, so we need a way to look up the public keys where we can trust those public keys, right? Okay, how? 8 minutes. So before we talk about how do we find a trusted source for getting public keys? So this is fundamental to the way security happens over the internet, how internet banking works. Everything works by doing this, being able to having a trusted source for getting public keys, right? That's core of what we do it. So before we discuss that, we need to know, talk about digital signatures. So what that means is that, so you guys sign documents with your signature, and if you sign a document or a contract, someone can take that to a court of law, right? And you can't then subsequently say, oh, it wasn't me, right? You can't say it wasn't me, yeah? Because it's called non-repudiation. That means I cannot turn back and say that was not me once you put your signature on a piece of document, right? Okay, so in the digital world, you have a similar concept. They're called digital keys, right? So you can digitally sign a message where you have the same property. That means a key can't be forged, just as in real life when you sign a piece of document with your signature, and you have non-repudiation. What that means is you can't turn around and say that's not my digital signature, right? So how do we do this in the digital world? Okay, that's what digital keys are all about. So essentially what you want to do, what happens is that Bob can use his private key to sign a message, right? Okay, and now the reason why this becomes a digital signature is because only Bob, right, in the world has this key, right? Nobody else does, right? So that means if Bob encrypts the message with his private key, only Bob can do that. Now, it's easy to verify that it's Bob. All we need to do is use Bob's what? Uncle? No. Bob's public key, right? Which is available to everyone, okay? So if anything that Bob has signed can be verified simply by using Bob's public key, right? Which is available to everyone, okay? So we can use a public and private key crypto system to sign messages, right? Okay? So Bob's message M, Bob takes his private key, right? Then encrypts it. Remember, it's always a private key. Please don't forget, okay? Because this is the secret that only Bob knows, right? And then your signed document is this guy. So your signed document is your message, right? And this encrypted version, right? Okay. So this is basically your signed document, right? Okay. In this case, it's the letter plus the encrypted version of that letter with Bob's key, right? Okay. Now, if Alice gets the message, then all Alice needs to do is use Bob's public key, right? Apply Bob's public key KB, right? And then check that she can recover M, right? Okay. So I take the message that I got, then I use the encrypted version, I decrypt the encrypted version using the public key, and check that the two messages are the same, right? So that you know that that message was signed. So this does three things. So that means the message is verifiable and non-forgeable. Because Bob signed M, no one else can sign M because Bob's the only one with the private key. And Bob could not have signed a different message, right? Why? Because we compare M with the one that we recover, right? Okay, we can compare the two together and see that it was not changed, right? So this allows non-repudiation, which means Alice can take M and the signature, which is this thing here, to court and prove that Bob signed M, and Bob can't say it wasn't me. Okay, is that clear? Right? So, unfortunately, it turns out that if you have a very long document, I don't know, 5-6 pages, and you want to encrypt it using public key cryptography, this is time-consuming, and it generates a very large output, right? So the one way to solve this is to use what's called a hash function. So you've heard of a hash because you may have done hash maps in data structures and algorithms, right? Order one lookup, right? Okay, so same idea, right? So what we do is to be able to, what we want to do is to shrink this message to produce a fixed size message. It's called a message digest, right? Okay, so you want to get a digest of the message. The way we do that is we take a large message and put it through a hash function, right, which creates a fixed size output, right? Okay, so this overcomes a computational problem. That is, instead of having to encrypt these very massive messages in public key cryptography, which is slow, now we just take the hash, right, of that. Okay, maybe you've downloaded programs, you've seen the hash computed, right? Imagine if you have to encrypt the whole program instead of the fixed size message. It's just a lot of work, right? And trying to decrypt it again, okay? So using a digest of the message just simplifies that process, okay? So there's a whole bunch of properties of hash functions that's really important. I guess one thing I want to talk about is this, right? So here's a property that's important. Think of the internet checksum. Say internet checksum is the way we generate a hash function, right? So this is not a very good hash function because what you can see is that if this is the message, right, that you create, what you find is that it's easy to take the message, change the message, and get the same hash value, right? Okay. So if you use internet checksum as your hash function, there's a weakness in that it is possible to find another message that's different, which generates the same hash, right? Now this is a security weakness because what that means is that I could potentially change the letter that Bob sends, I love you, to I don't love you, but I love you and I don't love you end up having the same message digest, so that when Bob gets it, he will verify that that was indeed the correct message, right? Because two messages are leading to the same hash value, right? That's called a collision, okay? So that's not a property you want to have, right? Okay. So, but there are better hash functions out there, but this is one thing you want to avoid. You want to make sure that the hash functions that you're using don't have collisions, or at least those collisions don't lead to a meaningful message, right? So that somebody can substitute two messages, right, without altering, let's say, the digital signature. See the problem? Okay. So look, I definitely am going to need another lecture, so that's cool. I'm happy with that. I hope you guys are. Sorry. So there was MD5 is a hash function that was used, and they found a collision for MD5, which is two different messages that lead to the same hash. But it turns out that the second message was kind of meaningless from the first one, so it's not too bad. But so MD5 is still being used despite the fact that there is a collision. But if you wanted a standard hash function, the recommended one these days is SHA version 3, right? Secure Hash Algorithm 3, right? So that's kind of what people are using, right? So, but you got to keep your eyes out. Maybe they'll find a collision for this one as well. Right? Collision means two different messages that leads to the same hash value. Okay. So what's the plan, guys? Do you guys want to